I'm going to make a quick detour into surface finish. So I added to the title block this surface finish callout. Given that we have all of our standard tolerances in place, and the surface finish has come up a few times in the last couple weeks with my machining. So we're going to take a look at what this symbol actually means. So unless otherwise specified, the surface is a 63 to 16 micro inches, the all around, and then the sample area is the 20 thousandths in multiple directions and up to 100 thousandths, so it gives a range. And then the waviness is 2 thousandths per 1 inch. Right, so what that ends up doing, if we want to add that symbol, that went a little too far, annotation, note, and I can add this to my drawings to tighten that up for specific areas. So once I place the note, and we can go pick the surface finish call out, and this is going to tell us what the symbols are, what they mean. So machining required, and then now we get it, machining prohibited. So if you're dealing with a cast part or a raw stock part, and those areas need to be controlled in such a way you have those available. JIS is a standard. We're not really doing much with. Maybe somebody will explain those to me someday. A local surface finish and all around. So if I apply the all around, it will put the circle at the top of the mix. And then maximum roughness, a minimum roughness, which we did encounter quite a while ago. An O-ring surface, a dynamic O-ring, that the machine tool that we used was actually able to generate very close to a mirror finish, a 16 to probably mid-20s, definitely between 16 and 32. And the O-ring slips so easily that the lubrication and the tolerance clearance, it really didn't seal. It didn't have enough bite to seal on the face. So there are times where we would want to go 32 to 63 and say, do not make this finer than a 32. Highlighting material removal allowance. So if I was machining this to go to a grind that I wanted to go finer than A16, getting down into the eighths, with the finish, I might put this on a surface grinder and be able to machine to a higher tolerance limit. So if it's a half-inch piece, maybe I would machine it to 5 thousandths over, so I don't have too much material to grind, but it's within the flatness and the ability of the grinder to remove that material. And then we get to the production method treatment. We'll take a look at the tech drawing description, but we're doing that, we're using that for waviness. And then the sampling length, 100 thousandths, and then the other roughness values, and then the roughness spacing. And then lastly was the directions that we're going to, basically if it's a grain or if it's in an area that we're wanting to measure. So I said 16 or 60, 63, so it goes basically in increments of 8. So 8, 16, 32. For whatever reason, no 64. It goes to 63 and then 128. And 128 is kind of in that saw cut. So a lot of times this will dictate processes as well. The machinist still has to make the decision of how to achieve that finish, but it gives a start for the build. So we did 0.1. I'm just going to reproduce what I had, 0.02, with a multiple direction callout. All right, so that's way more complicated than it needs to be. I could probably, for most surfaces, get rid of all of those and just say I need a 32 finish on this surface. And if we even went to the all around, within that callout would give me a decent finish to work with. All right, and then if I was going to use this common, whenever you see the styles, we haven't really done anything with favorites or with saving these add or update a style. So this is my 32 surface finish. And I'm not sure where it's saving those, so we'd have to go back up to the options, file locations, see where it's placing them. So once I've added that, there it is, then I still have to save it. So I can navigate back to my folders, my system, and 32, and save. All right, so if I have more than one surface that I want to apply that to, I can just pick it and place it for the geometry. And then I do have to watch, for some reason, if I click, there it goes. There are shadow surface finish callouts that get into the mix. All right, so what does all of that mean is this is a VM6 Haas Machining Center, and this plate is about 60 inches by 34, I believe, and just under an inch thick. So part of the subplate and tooling plate geometry is to get this flat and allow that if we overcut anywhere from 2 to say 5 thousandths, sometimes a little deeper, into the plate, it's a sacrificial plate. It pays for itself to go through this process by having a clamping surface that is able to be flattened and to make the setups a lot easier. So dowel pins are put in to locate the flat, large surface is our primary, and then we usually put in 2 pins across the secondary and then 1 pin for the tertiary, and that will create our datums for establishing those geometries. All right, so this gets clamped down with socketed cap screws into the T-slots on the machine table, and then kind of see the pins, and I have an alignment tool that gets it pretty much within 5 or 10 thousandths to start. And then we put a dial indicator on it, and this is a 0.0001 indicator. So 1/10 of a thousandth for each of the small marks. 0 to 1 is 1/1000th of an inch, and the total range is 16 thousandths, I believe, 8 thousandths in either direction. So we run it back and forth. So 0 there at the high point of the pin, and that is within 4/10 over 60 inches. So that's pretty close. And then we tap it a little bit and go back, and now we're within 2/10, and tap it a little bit, and legitimately we can say it's within 2/10. So these get snugged with a standard Allen wrench, but then so that everything is consistent, so that there's minimal amount of warpage in the torquing of the socketed cap screws. We'll use a torque wrench and torque them to about 60 to 70 foot-pounds. I don't remember what I use. It doesn't have to be extremely tight, but I want them consistent. And a couple more pictures, and there's the little tool and the dowel pins. So this has a 3-inch spacing of dowel pin holes and 1/2-13 tapped holes to perform the mounting. So to make sure that this is flat, this uses a 5-inch 8-flute facing mill, and this spins at about 800 RPM and moves at about 10 inches a minute. So if we run coolant, it's a lot of splashing, a lot of thing, and we'll take probably about 5/1000ths off just to take those previous sacrificial cuts out of the top surface. If this is something that it was already a finished part and I didn't want to splash with the coolant, oh, and that's the test indicator on the vise. So not quite ready for that one. Yeah, I would use the air nozzle and blow the chips away so that we could clear the parts. So when we do the 3D printing, you're kind of at the mercy of the resolution of the 3D printer. And then the finished surface is kind of this mirror, and we've raised, well, lowered the deck, but raised all of the grooves and surfaces to make this a very flat, smooth surface. So if I run the indicator across that, you're going to see that, see, is that the deck? That looks like the deck. So bring that down until it touches. And then as it, I think that's the vise, so I think I'm one ahead of myself. Yeah, that's the vise that we're trimming up. All right, so if I run the indicator across the 60 inches back and forth through a sampling, I will get around 2 to 5/10ths of a thousandth on the surface. So when we go to cut a plate, then we'll get a 3/4 inch plate, for instance. And because of the clamps, the question I get is, why aren't you running the big 5-inch face mill on this? Well, I don't have a lot of room over here and a lot of room over here on the travel of the machine. So I'm running a small 1-inch, and I'm running it at a higher RPM and a higher feed rate. And that's going to ultimately affect the surface finish and the waviness. So 34 inches a minute. And the problem is that these clamps, unless the material is 1 inch or taller, I run the risk of milling into my fixture, into my clamp, rather than just machining the material. So on this side there are 2 pins and a couple pieces of brass for this material to bank up on. And on the other side are the downforce clamps that put a little, and I'm relying on the weight of the material and the little bit of pressure from those clamps and pins to hold this in place. So I believe it said 2200 RPM at 34 inches a minute. This tool is also, because of the ramping profile of the larger face mills, I can't take as deep a cut. So with this end mill, and also this is the air blast, so it's basically blowing the material, the chips that the tool's producing, clear of the tool, so it's not building up, and it's keeping the tool cool. So depending on the operation, we'll get several different types of surface finishes. So you can see how close that was. If that was a larger end mill, I would be buzzing across the top of the clamps, which is not a fun noise to hear while you're in that machining process. So as it gets to the edge, it overcuts just a little bit. And finishes out the cut. All right. So when we talk about flatness and topology of a surface, this is already cut, this material. So this side is the lower side has been cut and is a smooth finished surface, well within, I would say easily within the 5/1000ths standard tolerance range. And this material started at the middle, or this tool started at the middle of the material and has already made the concentric pattern, but these are higher spots and this is a lower spot where it's leaving the raw material. So as I go through this process, I'm trying to hold as close a thickness to the print as I can, at the same time that I'm getting this as flat as I can. So if I needed this to be 750 plus or minus 5 thousandths, and a flatness call out of 5 thousandths and a parallelism of 5 thousandths, those are pretty tight tolerances. I think this machine can hold them. So that being the case, I would have to start off with a much thicker piece of material. So as this goes through, we start off from the low side, and as I'm moving the table around, this is a half thousandth indicator, so each of the marks is 0.0005, and each of the long marks, so right now, from that low spot, I'm about 5 thousandths taller than the dip. Now, the rest of the surface is staying well within a thousandth of an inch. So this moves across, we get a little high spot, so it jumps up 2 or 3 thousandths and then drops down. So at this point I can safely say that this plate, even in its current condition, it has a tolerance zone of 10 thousandths on its flatness for this surface. And as it's moving, it's catching those little bit of ribs. So we're going to look at the diagram. So surface finish then are these small grooves that are produced by an epicycle of the tool spinning and moving in a linear direction. And the tool has variation, the machine has variation, loading, unloading. So the waviness becomes these lines where the tool overlaps. A larger tool on a machine that the head is trammed well will produce a flatter section, and these waviness lines will get a little bit further apart. So let's see if the pictures are here. So at the beginning, okay, so there's the backside, and when the surface gets that nice, anytime we move it, have to pick it up, we run the risk of dragging, and this was my directional marks, but we run the risk of scratching this this surface. And then the starting point moves through. The indicator again for the surface, running the backside, reducing that surface down as close as we can get it, and then there comes a point where it's acceptable. This was where that 5 thousandths drop, but those little, we'd call it a butter coat, the raw material of the aluminum, that little bit of scaling is going to have to be acceptable to not take any more material and build out the other piece. So this is a lab mounting board or breadboard to mount optics or other pieces to. So it has to be the flat and parallel, and also have again, like the subplate, a lot of mounting locations for pins to locate and holes, tapped holes to control it. And then a 3D print. So the 3D print, again, we're going to see the same types of things that with the plastics. We need being a pliable material, the surface finish of the 3D print is based on the resolution of the part, and so you kind of get what you get. There are things that you can do with the 3D prints and the finishing to get it, but for the most part, we're not going to have the same level of control. All right, so from the tech drawing book, then the roughness height and the waviness height. So the waviness is kind of that general larger area, where the roughness is going to be in as the tool is going across. The faster that tool moves, the larger those epicycles are going to be. And then a flaw would be a scratch. I missed with the deburr tool and drug the deburr tool across the surface, which never happens. And then the roughness width is the sampling area and the directions that you're measuring to. So you get into the the designations of the surface roughness, and dimensioning and tolerancing, geometric dimensioning and tolerancing starts with this: how close of a surface do you need? What is the machine tool capable of maintaining, and being able to control those finishes.